So let us start. So in the previous lectures,
just confirm.
we have considered
I make computations.
quantum ideal gas,
Divide here and here,
and we have obtained thermodynamic functions
it's
of the gas.
So
We found
the grant U
thermodynamic
equals
potential
to
the
3
following
5 mu 0 and mu divided by mu sub 0 to the 5 power 1/2 plus 1 plus 5 pi squared over 8 theta divided
Here.
by mu.
M is the particle mass. Theta
Now
is
is
the
the
temperature.
question, why I
And
get
V is the volume. H bar is
because
the Planck constant.
at mu sub
And
0
here
are different
we have integral are different substances.
we have a relation
we have between mu
divided by the
and mu
exponent
sub 0
of x minus
we have derived
theta
these
minus
relations
plus
when we studied the dependence of chemical potential on temperature.
and we have
considered
no temperature
rarefied
dependence here, but we
quantum
have
ideal gas.
temperature dependence in ratio.
And we have found expansion
For granted,
and the exact form of dependence
potential
as follows. Is this
minus
we have derived this formula early.
f theta
And now
over 3
when I substitute this dependence, I know how here we unit and here small correction. And now I use the formula 1 to the x to the power 1/2
and here
is equals the 5 seconds over x.
1
And x is the small
Plus.
correction. I get
this means print 350 mu sub 0 n. Here I have exponent 1 plus 5 divided by theta over 2 here, 1 plus minus.
Okay.
5 over 24 minus 5 over 24
over
pi
half
squared
square root of
2 second power here 1
divided
plus to the
by
5/8 pi squared
And this expansion works
to the second
in
power.
the case of
And then I open
if
this bracket and I keep
ratio
track only of mu divided by
the
theta
terms that do not
is a
depend on
big
temperature
and the
negative
first
number.
leading term that is squared in temperature. So I have
So if the gas is rarefied, we can replace
and
the chemical
and here 1
potential
plus
by the classical value of
5
chemical potential
12
and
of pi squared
here this exponent
temperature divided by
equals 2
to the
here
gs
gs.
to the second power.
Okay,
And this is
GS
the estimate
is the spin
for the
this is the estimate for the
internal
energy. And we see that 0 sub 0 is temperature at 0 temperatures. We have the internal energy at 0 temperature has the form this one. Okay,
Theta.
at this point we finish our lecture. If you have questions, you can ask me if this ratio is much less than 1. If this condition is true, we have a quantum gas which properties slightly different from that of classical gas. And this term, which is small, it controls it gives a first quantum correction to the classical expansion, classical contribution to the classical ground thermodynamic potential. Now, we are interested in an opposite case. We can see that and let me stress, this condition is true if the temperature is quite high enough the particles are heavy, big mass, and ratio n divided by v, so its particle concentration is quite small. Now we consider opposite case. We assume that this ratio, this dimensional ratio, we have interpreted this ratio as the average number of particles in quantum state if it's comparable to unit. Let me write this way. Gas in which such relation is satisfied are called degenerate gases. Are called degenerate gases. As we see in the degenerate gas, quantum corrections are very high. So the properties of the degenerate gas should be very different from that of classical gas. Now we can, and looking at this formula, we can find conditions such that the quantum gas can be degenerate. So when this ratio can be big, the first ingredient is the particle concentration. So the first option is it is a dense gas. By saying dense, I mean that ratio n divided by v is very big. So it's very dense gas. It's not, it's much denser than in usual conditions. The second option is the low temperatures. If the temperature is low and concentration is normal, we can make this ratio big. So cold gases. I mean, by saying cold, I mean cryogenic, so very cold. And the third option is the light particles. Why light particles? Please look here, m in the denominator of the fraction. This means that for light particles, this ratio can be very big, even if the temperature and concentration are not high. This means that the quantum corrections are very important for the gases of light particles. From physics, it's quite natural because quantum effects are very strong for microscopic objects. So the lighter particle, the stronger quantum corrections. And all these three cases appear in the real world. And the first option, I mean dense gases, we face in astrophysics. This is so-called degenerate stars. I mean here white dwarfs and neutron stars. As we know, the gravitation pressure in these stars is compensated by the pressure of the degenerate gas. And both these types of stars have very high density. White dwarf, the density of white dwarfs 1,000,000 times higher than the density of Earth's matter. And here we have density 15 orders higher than our usual matter. So here density of matter like 10 to the 6th power grams in cubic centimeter. And here on the side. Now, cold gases, we see effect of Bose condensation. And light particles, the well-known light particle is the electron. So the most interesting case is the cases of electrons. Please note that in the first case we usually have Fermi statistics. Here we have Fermi statistics, and here we have Bose statistics. In most interesting cases, of course, we can consider cold gases of fermions, but is it okay? It may be interesting in fermions also. And these two cases are mostly important for fermion cases. As we see, the case of fermion gas is the most interesting, and it is much simpler than the Bose gas. So we start our consideration from gas of fermions. So let me try to keep on the whiteboard. Okay. Okay, I want to keep these letters. The subject of our lecture is degenerate Fermi gas. Okay. And so, if we can reference.
U mnie pana było teraz, zaraz ciebie porozmawiać. Ja to Karol, tak. Ja to jest transpara.
Dear students, please switch off microphone. Thank you.
Ja надеюсь, że z dokładnie.
Okay. Now we consider Fermi gas. Once I said Fermi, this means that the spin of the particle is half integer. And so on. Of course, the most important case is spin equals to 1/2, and this corresponds to electrons. And we start our consideration from the study of the shape, from the study of Fermi statistics. we know that for fermions, the occupation numbers, the average occupation numbers are defined by the formula here. I put the sign plus because I have fermions. And I'm interested in low temperatures. So I may consider an extreme case at first. Theta tends to 0. In this case, I have very special form of dependence of occupation numbers on energy. So let us first take very small energies. Let's say equal to 0. If we expect that for small energies, this difference is a negative number. So epsilon is less than mu. In this case, I have a certain negative number divided by something very small. This exponent is very small quantity. So I set it to 0. I set it to 0, and then I have 1 divided by 1, it's 1. Epsilon less than mu. Here, I should emphasize that the chemical potential depends on temperature, in principle. So I should, when I consider limit of 0 temperatures, I should take the value of chemical temperature at chemical potential at 0 temperature. So, okay. I introduce a special notation, mu sub 0. If the energy is high, this difference is a positive number. Because energy of the particle can be very high, so we have positive number. Positive number divided by 0 or very small number, it's a big positive number. And this exponent is very big. So plus 1, it's a very big number. And 1 divided by something very big, it's 0. Please, left one string intentionally blank and put 0 here. Epsilon is greater than mu sub 0. And finally, we have intermediate case, epsilon equals to mu 0. In this case, exponent equals to 1, and here I have average occupation number 1/2. Now I'm going to make a plot of this function, m of epsilon. Here, I out right energy axis, and here, average occupation number. I put unit here. And please write the line n equals to 1. And mu sub 0, it's certain value of energy. Okay. Sub-zero. This formula says that the occupation number equals to 1 when the energy is greater than nu sub-zero. For energies higher than mu sub-zero, we have 0. Okay. And here, I need to write 1/2. Have a special point, 1/2. So I have this interesting shape. It's very different from that of the classical case. So we have a gas with a different properties. The function n of f, n of epsilon have a ladder shape, ladder ступенька, ladder shape. So it tells me that all the states that have energy less than mu zero are occupied, and all the states with energy higher than mu sub zero are not occupied. Okay. We also, and we can easily, and in this case, we can easily find the number of particles in gas. It equals to the number of states, number of quantum states that have energy less than energy mu sub zero. Once we have many particles in gas, or let's say at least one particle, at least one particle in gas, we have to make a conclusion that when that chemical potential mu sub zero is a positive number. In thermodynamics, the value mu sub zero is known as the Fermi energy. As we see, at zero temperature, Fermi energy is the energy of the state that has occupation number 1/2. The shape and this special form of distribution will change only slightly if the temperature is less than mu sub zero. Now, we assume that temperature divided by mu sub zero is much less than 1. So, what we will have? This exponent changes its value from 0 to infinity in the range theta minus in the range mu sub 0 minus theta to the value mu sub 0 plus theta. So if you want, you can make estimates. I will not detail these computations, but we can see that for such value, mu sub 0 minus theta, we have occupation number around 3/2. And here we have occupation number about 1/2. And here my plot tends to 1, asymptotically tends to 1, and here it tends asymptotically to 0. So I have the shape of the occupation numbers curve like the ladder, but now it's not maybe rectangular, but it has a smooth transition between occupied states and empty states. We see and we can see that the shape, that this ladder shape of the curve will remain valid until delta mu divided by theta divided by mu sub 0 equals to 1. Maybe less than equal to 1. And this and the temperature theta equals mu sub 0. Let me recall that we used energetic scale of temperature, so the temperature has dimension of energy, and mu sub 0 is an energy. And this temperature is the temperature of degeneration of Fermi gas. If theta less than theta, temperature less than theta asked, gas is degenerate. Gas is degenerate. Now, okay, and we are interested in the thermodynamic properties of degenerate gas. We are interested in thermodynamic properties of degenerate gas. I'm going to explain these properties for all the temperatures in the range theta from 0 to the temperature of degeneration. In some cases, it may be convenient to consider 0 temperature and later non-zero temperature. I want to consider all this range of temperatures in one time. And I'm interested in thermodynamic functions of degenerate gas. These functions are pressure, internal energy, particle number. It's very important because I want to express chemical potential in terms of particle number. And maybe heat capacity and entropy. It's very easy to write down these two functions. We know a couple of identities. First, we know that the pressure is minus omega divided by V. And we can easily write an expression for this quantity.
Okay, and here is integral 1 to infinity x to the power 3/2 the x, and here is integral over x minus mu over theta. And here I put plus because I consider only fermions. This formula, this relation between pressure and ground thermodynamic potential is general. Okay. Yeah, mistake. Is general. It's true for a general gas, degenerate, or non-degenerate. In case of precious. In case of internal energy, we have another relation. U equals to the 3/2 of PV minus or 3/2 of omega. And again, we can easily find the expression. Now, I don't need 3, I have 2, and I'll cancel 1, 2 here. So 2 m theta to the power 3/2 V divided 2 pi gs. I forgot gs here to the third power. And here I have the same integral. Okay. Okay, here, and now I'm interested in the particle number. I will write out the formula, and you can find this formula in one of the previous lectures. So n equals to gs 2 pi 2 m theta to the power 3/2 to h bar cube. Okay, this here is mistake. Here should be theta, and here should be v without theta. Okay, and here is an integral x to the 1/2. Please note here 1/2, here 3/2 to the exponent x minus mu by theta plus 1. In principle, we can write out the expressions for entropy and heat capacity, but they can be computed very easily. The heat capacity is a time derivative of internal energy for constant V and N, and entropy is a minus derivative of ground thermodynamic potential with respect to the temperature. Okay. So if we find P, U, and N, we will find heat capacity and entropy. It's not a problem.
Извините, пожалуйста, а мы не потеряли минус при поиске внутренней энергии?
Okay, it's correct. Correct. Thank you. I write very small minus here, but it should be very big. And here should be big minus. Okay, thank you for the comment. Now, and when we considered general quantum gas, our problem was that these integrals cannot be computed explicitly. So we had these expressions only in implicit form. In case of degenerate gas, these integrals can be estimated. And our first task is to estimate these integrals, this, and this. I will not consider. So to solve the problem, it's better to consider a more, okay, no, it's not correct. And the problem suggests that we need to consider the integrals of this form. 1 to the infinity, f of certain argument x dx divided by x exponent x minus mu divided by theta plus 1, where f of x equals to x to the 3/2, or f at x equals to 1/2. And we remember that gas is degenerate. So the exponent mu over theta is much bigger than 1. So chemical potential is big with respect to the temperature. And it's the same that the chemical potential divided by theta much bigger than 1. And now I'm going to make an asymptotic estimate for this integral. Okay, let us continue. At the first step, I introduce a new integration variable. I will denote it by z, and it will be equal to x minus mu divided by t. In fact, it's an argument of exponent. The integration measure is preserved by such change of variable. So, I get something like this. I have x is replaced by z plus mu divided by theta. And I will write mu divided by theta first, and z second. And here I will get exponent of z plus 1. The upper integration limit equals to infinity, as in the previous case, but lower integration limit now is minus mu divided by theta. And at the next step, I divide this integral into two pieces. One integrates from 0 to infinity, and other integrates from mu divided by theta to 0. Okay. Plus This integral is what I want to have. And this integral should be transformed. Now I transformate the second integral. Plus that. And here I make the change of variable from z to minus z. And I get something like this. The lower limit is 0. When I replace z to minus z, I have a total minus in front of integral. So I change integration limit to absorb this minus. Here I have this f divided by theta minus z of exponent, here minus z plus 1 dz. And now I transform this exponent. 1 to the exponent to the minus z power equals, I multiply both the fractions, both the lower and higher part of the fraction, on exponent to the power z. And then identically rewrite it as 1 minus the exponent to the power z plus 1. Substituting this expression, I get the following. Integral to mu divided by theta f f of mu divided by theta minus z dz. Okay, and here I get minus integral mu over theta f of mu divided by theta minus z, now exponent to the power of z plus 1 dz. Now we can substitute this here. And we can identically rewrite the interesting integral in the form. Okay, I make one little simplification. When I make one little specification, I replace z here by x equals z plus 9 divided by theta. And in this case, I have integral of f of x. No, it's not correct. Divided by theta dx. Plus, I rewrite this part. 1, 2, plus infinity f of mu divided by theta plus z dz 1 and minus integral 1 mu divided by theta and mu divided by theta minus z as power c plus 1. This form of integral is exact. We not even a small simplification. Now we are going to make a simplifications that lead to the expansion for this integral in small parameter, in small parameter theta divided by. And the first simplification is that I replace here mu divided by theta by infinite limit. This is not this is very good approximation because this integral converges very fast. Please look here, exponent, and here some maybe polynomial function. So it's very good approximation. In this case, I can join these two integrals into one integral. Okay, into one integral. Okay, and here it is it. And another important observation is follows. Once exponent grows very fast for big Z, we are interested. We should interested in the contributions. With small z, which are most important. Which are most important in this case. So we have to expand. We have to expand this function in the Taylor series at z equals 1, at z equals 0. So I'm writing an expansion for the Taylor series equals here. Okay, I will write square bracket, and this one is this guy. I will put in the square bracket here. The second in this square bracket, and this in another square bracket. So please note that zero order vanishes identically. When I put z to 0, I have f minus f, and this is 0. So I had to keep track at least the first order in Z. So I write to the first order as f prime. Prime means derivative of a function by its argument. Here some high order corrections which are not interested for me. And here minus. So I will get first order correction with sign minus. Plus some higher contributions. These guys cancel each other, and I get 2f prime mu divided by theta z. Please note that f prime of mu divided by theta doesn't depend on z, so it's constant. Now we can write out the estimate for the integral in question. Yeah. Integral from 0 to divided by theta f of x dx. And here I will have first order correction, which equals to 2 f prime mu divided by theta. And here is integral from 0 to plus infinity z dz e exponent to the power z plus 1. Okay, this integral cannot be computed in. Okay, this integral has a tabular value. I think I don't have time to demonstrate the computation of this integral. If you ask me later, I will make such demonstration. It equals p squared over 12. And now we have a final form of the expansion of the integral in question. Pi squared over 6. Okay, not here. It's better to write here. Pi squared over 6. Let me consult my computations. Let me consult my computations. Is it okay? Or not? Okay, it's correct. In principle, we may have higher corrections. To find these higher corrections, we should make a Taylor expansion, not up to the first order, but up to the third order. The second order will cancel each other. It's not difficult to observe this fact. Now we can give an interpretation to this structure, to the structure of the obtained expression. Here we have the value of physical observable at theta equals 0. Please note that this integral does not depend on theta. And this is the first order correction. The first order correction to the zero temperature value of this integral. As we consider a degenerate gas, we assume that the correction is small. The correction is small, and its value is much less than the value of zero temperature contribution. Okay. The interpretation of this correction in the small value will help us with simplification. Okay, I need these formulas. So, okay. No, it's not good. So you have the formulas in your textbooks, in your copy. So I right, erase here. So let me ask, should we make a break, 5-minute break, or not?
Ну, может, раньше лучше закончить.
Okay, without break. We continue without break. And now we are interested in thermodynamic functions of the degenerate gas. At first, we consider the particle concentration. Okay, the particle number. So we have the particle number is determined by the formula n equals to gs 2 pi m 2m theta to the power 3/2 v divided to ph bar to the third power, and here integral from 0 to infinity x to the power 1/2 dx exponent to the power x minus mu divided by theta plus 1. In this case, we have function f of x equals to the x power 1/2. And its derivative has the form f of x prime of x equals 1/2 to the x to the power 1 minus 1/2 minus 1/2. And I have prime of mu over theta equals to 1/2 theta over mu to the power 1/2. Okay, we have ingredients and use this formula. And because, okay, we write all from here. And here I have first integral f of x. F integral f of x and x to the power 1/2 dx from 0 to mu divided by theta. And here I have the first correction. It's pi squared divided by 12 theta divided by mu to the power 1/2. We can easily find.
А почему мы делим на 12, а не на 6? У нас разве не сокращалось?
Please look.
А, да, спасибо, поняла.
Okay, and now we should compute this integral. It's very easy. So I replace this integral by its value. It's 2/3 of mu divided by theta to the power 3/2. And it's better to, and now we can just take the leading term as a common factor, and then in bracket we will get 1 plus certain correction. So So we will get n equals to gs. Here, 4 pi 2m theta to the power 3/2 of v divided to 2 pi h cube. Here 3 mu divided by theta to the power 3/2. And here I will have 1. And now 2 cancel 2. Okay. When we take 3, we take 3 is a common factor. 3 cancels 3 in 12. And 2 multiplied by 4. So we have pi squared over 8 theta divided by mu is to the second power. Our interest is to express the chemical potential in terms of the particle number, or maybe particle concentration, because particle number is much convenient variable from the physical viewpoint. So, to do so, I make the following. I express mu over theta divided to the power 3/2. Okay. Mu divided by theta to the power 3/2 equals. Okay, I should divide by this guy, but I can use the simplification formula. 1 divided plus b squared over 8 theta divided by mu squared equals approximately 1 minus b squared over 8 theta over mu. Here, I use the fact that the ratio theta divided by mu is very small. It's much less than 1. So, in this case, I have 3, 2 pi h cube multiplied by n.
Дмитрий Сергеевич, а почему у вас там в квадратных скобках это разделить на μ в квадрате? Там же вроде 1/2 была.
Please look, this I used.
Ага, да, все понял, спасибо.
Okay. 4 pi 2m theta to the power 3/2 v. Oh, okay. And here somewhere g sub s. And now I divide it by this guy. It's the same to multiply by this one. 1 minus b squared over 8 theta over mu. Okay, let me write square bracket. Okay, I get something like this. So in the left-hand side, I have chemical potential. In the right-hand side, I have something that doesn't depend on chemical potential plus small correction. Once I assume that the temperature is much less than mu in the range of temperatures of interest, I can assume that okay, I can solve this equation order by order. At the first step, I set temperature to 0. And in this case, I find, okay, it's not good, it's too fast. Okay, and I want to express, and now I want to express mu over theta. Okay, 3 to pi h to the power 3 by 4b gs 2m theta to the power 3/2 v. And now I need to do the power 2/3, and now I need to use Taylor series extension one more time. 1 of pi squared 8 to the power theta over mu squared in the power 3/2 equals 1 minus pi squared over 12 theta divided by mu to the power squared. So I get something like this. 1 minus p squared by 12 theta over mu squared. Okay. Please note that here theta is to the power -1, and here again to the power -1. So I erase theta. And this is a equation which can be solved. At first step, we take 0 temperature. In this case, I found the Fermi energy 3 to the power 2 pi h power 3 and 4 pi gs to m to the power 3/2 v. This expression can be simplified, but I do not want to do this. This step I get the Fermi energy, and now I consider this guy as a small correction. Once this correction is small, and once I believe, this means that the value of mu and value of mu null and mu sub 0 are very similar. In this case, without loss of precision, I can replace mu by mu sub 0 in the second approximation. So I found mu equals mu sub 0 multiplied by 1 minus pi squared over 12 theta divided by mu sub 0 to the second. I have expression for mu sub 0 as a function of model parameters, and here the expansion for mu. Okay, this is very useful formula, and it tells me that the chemical potential of the Fermi gas, it tells me how chemical potential of Fermi gas depends on temperature. Okay, should I replace? No, I have no time to express mu in terms of n, v, and substitute here. Let us remember this formula. Okay, now we are interested in internal energy. As we know that the pressure and internal energy are related to each other, finding internal energy, we can find the pressure. So I'm interested in internal energy. The formula for internal energy is given here. And the integral of interest corresponds to the choice of function f of x equals to the x to the power 3/2. In this case, f prime of mu divided by theta, f mu divided by theta equals to the 3/2 mu divided by theta to the power 1/2. And one very important is the integral of from 0 to infinity of f from 0 to mu divided by theta of f of x, the x. It's very easy to find this expression. So x to the power 3/2. So we have 2/5 mu divided by theta to the power 5 seconds. And using the formula which we derived, we find u equals to q by gs g by 2m theta to the power 3/2 theta v divided by 2p h bar. And here in the bracket, I have 2/5 of mu divided by theta, 2/5 of mu divided by theta to the power 5 seconds. And here I have plus 1/4, not fourth. Oh, okay, just let me look. 5. 1/4, because here 1/8, but when we have here, it will be 1/4. P squared divided by 4 to the power mu divided by theta to 1/2. And now it's too convenient to take classical contribution as a common factor. So we get gs 2 pi 2 m theta to the power 3/2 theta v 2 pi h bar to the third power. Okay, it's 4, here 4, here 4, and here 5. Mu over theta to the power 5 seconds. And here 1 plus 5/8 mu over, okay, not mu over theta, but theta over mu to the power to the second. Now we expressed the internal energy in terms of temperature. Okay, in terms of chemical potential and temperature. Now we are going to express the internal energy in terms of in terms of particle number. So we should use okay. I'm thinking how to make a better, just to simplify. Okay, just to simplify. So what we should do? We should substitute this value of chemical potential here and here.
And I do a little simplification. Instead of direct substitution, I will write here mu divided by theta to the power 3/2 and mu divided by theta here. And we know that mu divided by theta to the power 3/2 looks almost like this term with some, maybe some common factor. And when we substitute here, I mean here, we substitute here, we will get u equals to the 3/5 of mu n. Oh, okay, 3/5. Okay, okay, mu sub 0 n. Please look that here is a mu sub 0. It's better to put mu sub 0. And it's a constant. Now, and then I have, and then I have okay. Just let me think how to better. Yeah, I have mu n. Okay, just let me think how to make it better. Okay, I'm looking at the temperature. Okay, so here mu sub 0. And then, okay. Oh, okay, I know what to do better. How to do? Please look that. Please look that here all the temperatures cancel each other. So I can cancel temperatures. And then I substitute mu sub 0, mu sub 0, mu sub 0 to the power 5. When I use mu sub 0 is some constant whose value is very good known to us. When we substitute mu sub 0 in terms of n, we will observe that this guy, except one of this mu, is proportional to n with some factor. The exact comparison will gives us 3/5 of mu sub 0 n. And here I have dependence on mu here and here. Without losing precision, I can put mu sub 0 here and expand this ratio in the Taylor series. So I divide it by mu sub 0 here, and then take to the power 5/2, and I give the approximately 1 minus 5/24 pi squared over theta divided mu sub 0 squared.
So I replace this ratio, 1 minus 5 to the power 24th. Here pi squared, the theta divided by mu 0 to the power. When I open these brackets, I need to keep only quadratic part in temperatures. So, and temperature independent term. Temperature independent term 1. And when I combine here, I get 5 over 8 minus 5 over 24. It's 15 minus 5. I compute the coefficient at pi squared theta over mu to the second power. 5 over 8 minus 5 over 24 multiplied by 3 and 10 to the power 24. And here divide by 2, 5.
Дмитрий Сергеевич, можно спросить?
Okay.
Что-то непонятно. А как мы вот μ на μ нулевое в степени 5/2, откуда у нас там тета взялась? Мы же ее сократили, и вы в итоге заменяете вот это μ на μ нулевое через выражение, в котором есть тета, хотя мы его уже сократили везде.
So okay. Please look that I cancel theta. I cancel theta only. Okay, I cancel theta only in the prefactor. I do not cancel theta in the bracket. I do not cancel theta in the bracket here. So.
А вы, кстати, так и не сказали, почему нам, когда мы μ на μ нулевое 5/2 мы раскладываем, и у нас снова тета возникает. Хотя мы откуда?
Okay. So let me just confirm. Then I make computations. I see divide here and here, and I see here it's 1. So I have u equals 235 mu 0 and mu divided by mu sub 0 to the 5 power 1/2 plus 1 plus 5 pi squared over 8 theta divided by mu to the power. Okay. Now it's your question. Why I get theta? Because mu at mu sub 0 are different substances. We have a relation between mu and mu sub 0. We have derived these relations when we studied the dependence of chemical potential on temperature. So we have no temperature dependence here, but we have temperature dependence in ratio mu divided mu sub 0. And the exact form of dependence is this. We have derived this formula earlier. And now, when I substitute this dependence, I know how. Here's unit and here small correction. And now I use the formula 1 to the x to the power 1/2 is equals to the 5 seconds over x. And x is the small correction. I get 350 mu sub 0 n. Okay, 1 plus 5 over 20. Okay, 5 over 24 minus 5 over 24 pi squared theta over mu to second power here 1 plus to the 5/8 pi squared the theta over mu to the second power. And then I open this bracket and I keep track only the terms that do not depend on temperature and the first leading term that is squared in temperature. So I have 3, 5, mu sub 0, and here 1 plus 5 twelfths of pi squared temperature divided by mu to the squared to the second power. And this is the estimate for the internal energy. And we see that O sub 0 is the temperature at 0 temperatures. The internal energy at 0 temperature has the form this one. Okay. At this point, we finish our lecture. If you have questions, you can ask me